different problems that can be asked in BJT or in timer. Okay, so before that, let's see what type of questions can be asked in this particular module. Okay, so you can expect questions like, with neat circuit diagram, explain how transistor is used as voltage amplifier. This is nothing but under the topic BJT as an amplifier. Derive the equation for gain. Okay, and then you have voltage series feedback circuit and derive an equation for voltage gain AV with feedback. Then we have with neat circuit diagram, explain how transistor can be used to switch an LED on or off with necessary equations. And then you have a problem here with the common emitter configuration. This is one of the question paper I've put here. One more question paper, they have asked, what is feedback amplifier? What are the properties of negative feedback amplifier? Okay, so explain how transistor can be used as an amplifier, and with neat circuit diagram and waveforms, explain the working of 555 timer as an oscillator. Then draw the block diagram of voltage series negative feedback amplifier, derive the equation for voltage gain, design an RC phase shift oscillator that comes under oscillators, then Wien bridge oscillator. Okay, so you have three portions, that is oscillator, RC phase shift, and Wien bridge will be done in the next session, but other rest of the part of the question, everything we have covered. In one more question paper, again the same question, that is BJT as an amplifier, then voltage series feedback circuit, derive the equation for voltage gain, RC phase shift oscillator, and transistor as a switch, that is to on an LED. Okay, then a question on transistor, that is it is used as an common emitter configuration, and you are supposed to get the different parameters. Then explain the operation of IC 555 as an A-stable oscillator with neat circuit diagram and necessary equation. So if you refer all the previous question papers, so one important, all the questions that are being asked almost are repeated, and in that BJT as an amplifier is a very important question. Okay, to derive the equation from that, and also voltage series feedback circuit, and derive the equation for voltage gain, that is also very important. Yeah, RC phase shift oscillator and Wien bridge is also important. Then how transistor can be used as a switch, used to switch an LED, is also important. Then related question, then IC 555 timer. So these are few question papers I have put here, so you can refer the question papers and you can find out that almost these topics are very important. And voltage series feedback amplifier circuit, I'll be explaining again in this session, because in the previous session we have just as a comparison with the different types of topologies it was explained, and here I'll be explaining in just as voltage series feedback circuit. Okay, so I hope whatever problems we solve here and whatever the questions being asked, the thing is you will be understanding properly and will move forward into the session. Okay, now one question here is, determine the voltage gain and AC output voltage if R dash E is equal to 50 ohm. This is a question from BJT as an amplifier. Okay, so here you can see the circuit is exactly how BJT is used in an amplifier, and here the parameters are given. So we have already found the equation for gain using amplifier, that is AV is equal to RC divided by R dash E, where RC is the collector resistance of the collector, and R dash E is the internal AC resistance or internal emitter resistance. Okay, so to find the voltage gain, we can directly substitute that RC divided by R dash E. R dash E is given 50 ohms, and RC from the figure we can find that it is 1 kilo ohm. So directly when I substitute, I'll get it as 20. And we are supposed to find the AC output voltage. How do we find AC output voltage? So we know that gain is nothing but output voltage divided by input voltage, right? So we can write A as V out divided by V in, right? So V out, we have to find now and we know we have already calculated gain. So what is v in? V in is nothing but the input voltage. What is input voltage here? It is the base voltage vb. So vb is already given as 100 millivolts. Substitute that, and gain we have got 20. So if you multiply that, we will get 2v rms. Since it is a AC output voltage, we need to write in terms of root mean square 2 volt rms. Okay, so this kind of question from BJT amplifier you can expect. Okay, let us see one more question. So this circuit, for the transistor circuit, what is VCE when V in is 0 volts? What is minimum value of IB is required to saturate this transistor if beta DC is 200? Neglect VCE. Calculate the maximum value of RB when V in is 5 volts. So if you see this circuit, it is exactly BJT as a switch, that is, it is working for the cutoff condition and saturation condition. And we have derived the expressions for when it is cut off, what is output voltage, and when it is in saturation, what is the output voltage. Okay, so we are here to calculate different types of parameters. So first, for the part A question, you have to, what is VCE when V in is 0 volts? So when V in here you are giving 0 volts, what is happening in the BJT? This is actually, there is no current flowing, no IB current flowing. So because of that, BJT is off. So V out will be equal to VCC, right? So there is a maximum voltage appearing at the output, that is nothing but, what is VCC? VCC is already given here, that is 10 volts. Okay, so the first question, when V in is 0, the transistor is in cutoff, acts like an open switch, and VCE is equal to VCC, which is equal to 10 volts. Okay, so next question, you are supposed to calculate IB minimum. IB minimum, we all know that IB is equal, IC can be calculated as beta into IB. If you remember the equation for BJT, so collector current is beta times the base current. Okay, so from this we can find IB minimum. What is IB minimum? We can find. So for that, first we have to find IC saturation. How do we find IC saturation? So VC is already in the question itself, it is given that neglect VCE. So from that we can write IC is equal to VCC divided by RC. That is the Ohm's law. Using Ohm's law we can write. So VCC is 10 volts and RC is 1.0 kilo ohm. So IC saturation, I will get it as 10 milliampere. Now when I substitute IC saturation as 10 milliampere and beta DC is already given 200, then the minimum base current that is required to make this particular, to drive to the point of saturation, is 50 microampere. Okay, so any further increase in IB will ensure that transistor remains in saturation, but there cannot be any further increase in IC. So after 50 microamperes, when we get into the point of saturation. Next question is part C is, when the transistor is on. Okay, so what is the what calculate the maximum value of RB when V in is 5 volts. V in is 5 volts means this transistor is in on state. Okay, transistor in on state. So we all know that VBE, that is the diode, whichever the diode we are considering, to make it conduct, it needs a small voltage drop, that is a knee voltage drop, that is nothing but VB, and usually for silicon diode it is 0.7 volts. Okay, so when the transistor is on, to get into the conducting stage, VB is 0.7 volts. So voltage across RB can be written as VRB is equal to V in minus VBE. So 5 volts minus 0.7, V in is 5 volts, 5 volts is minus 0.7, that will be 4.3 volts. So this is the voltage across the RB. Now to calculate the maximum value of RB needed to allow a minimum of IB, we are using Ohm's law. So Ohm's law we can write it as RB is equal to VRB divided by IB. So VRB we have already calculated, that is 4.3 volts. IB we have already got 50 microamperes. When we substitute that, we get it as 86 kilo ohm. So this question is almost asked many times. So I hope you have understood what is the different condition we have to take here when it is cut off, when it is saturation, and how to calculate RB max. Okay. So next question, in this question the LED requires 30 milliampere to emit a sufficient level of light. Therefore the collector current should be approximately 30 milliampere. For the following circuit values, determine the amplitude of square wave input voltage necessary to make sure that the transistor saturation. Use double the minimum value of base current as a safety margin to ensure saturation, and the given parameters, that is VCC is 9 volts, VCC is 9 volts. Okay, VCC is 9 volts, VC saturation is 0.3 volts. Okay, VC saturation is 0.3 volts. RC is 220 ohm, RB is 3.3 kilo ohm. Okay, and beta DC is equal to 50, and VLED, that is voltage across LED, is 1.6 volts. Okay, so to find IC, that is a collector current, first we have to using Ohm's law we can find what is that. So we can, in this way, when we write, it is VCC, right? VCC minus what is the voltage across LED, VLED, minus this voltage, that is across collector and emitter, that is when it is saturation, VC saturation, divide by RC, we will get IC saturation. Okay, the current flowing from this circuit from the collector to emitter. So in that path, if we take the voltage, then it will be in this fashion: VCC minus VLED minus VC set. So VCC is already given as 9 volts, VLED is already given as 1.6 volts, and VC set is given as 0.3 volts. So from that we will get IC saturation as 32.3. So from that IB minimum we will get the equation, that is IC sat divided by beta DC. So that is equal to 32.3 milliampere divided by 50. So that is 646 microampere. Okay, so IB minimum we have got. Again they have told that use double the minimum value of base current to ensure saturation. So to ensure saturation we have to take the double the IB minimum, which is equal to 1.2129 milliampere. So when you double the 646 microampere, you will get 1.29 milliampere. So to find V in, we will use Ohm's law. So IB is equal to VRB divided by RB, and VRB is same as in the previous question we have written, V in minus VBE divided by RB. So V in we don't know, VB you know that it is standardly taken as silicon diode 0.7 volts, divided by RB is 3.3 kilo ohm. It is already given. So from that we can write V in minus 0.7 volts is equal to IB is written as 2 times IB, because it is already given here. Use twice the value, 2 times IB minimum into RB. So that is 1.29 milliampere into 3.3 kilo ohm. So when you write this equation, simplify this equation, you will get V in as 4.96 volts. Okay, so that is how you are supposed to find the V in voltage. Okay, so IC saturation equation here for LED, you have to take all the voltages across the path of the direction of the collect current, then you will get what is the saturation value. From that you can find IB minimum, and V in you can find from this equation IB is equal to VRB divided by RB. Substitute VRB as V in minus VB, then from that we will get what is the value of V in. Okay, so now one more question on astable 555 oscillator, that is a timer, is constructed using following components: R1 is equal to 1 kilo, R2 is equal to 2 kilo, and capacitor C is equal to 10 microfarad. Calculate the output frequency from 555 oscillator and the duty cycle from the output waveform. So 555 timer, we know that for the charging it will take R1, R2 and C, that path, and for discharging it will take C and R2. So we know that the capacitor charge on time, high time, T1 is equal to 0.693 into R1 plus R2 into C. R1 value is given as 1 kilo ohm, R2 value is given as 2 kilo ohm. So substitute that values here. Okay, so into C is given as 10 microfarad, so 10 into 10 to the power minus 6. So you will get T high or T on is equal to 21 milliseconds. Now capacitor discharge is using this equation, 0.693 into R2 into C. So R2 is given as the 2 kilo ohm, substitute that, and C is 10 microfarad. So we will get T2 as 14 milliseconds. We all know that the total time period T is equal to T on plus T off, that is T1 plus T2. So from that we will get T. Now we know that T and frequency is related. How is it? F is equal to 1 by T. F is inversely proportional to the time period. Okay, substitute that and we will get the equation for value for frequency. So total time period t1 we got at 21 milliseconds and t2 we got it as 14 milliseconds. So we will get the total time period t is 35 milliseconds. So to find the frequency, take the reciprocal of that, 1 divided by 35 milliseconds, and it is equal to 28.6 hertz. Now to find duty cycle, what we will do is take the equation t on divided by t. So if you take that equation, or t1 divided by t, then you will get r1 plus r2 divided by r1 plus 2r2, and 0.693 will get cancelled. So and c will get cancelled. So you will get the answer 1000 plus 2000 divided by 1000 plus 2 into 2000, or duty cycle you will get it as 60%. So this type of question can be asked with respect to astable oscillator that is using 555 timer. So you need to remember all the equations related to t high or t on, t off or t low, and find the frequency and duty cycle. Okay, so I told you we will be deriving voltage series feedback amplifier. So in case of voltage series feedback amplifier, you know that feedback circuit. So there is a feedback taken, and the input, it is the voltage is given in series. Okay, so here we have to see that it is a most of the case we are taking it is negative feedback, means we are going to give here minus. Okay, so whenever negative feedback is asked, we have to give here minus. Okay, so we know that the amplifier has the gain a is equal to v out by v in, and this beta is the feedback factor or the feedback ratio. So that is equal to vf divided by v naught, v out. Okay, so we have to find now what is the gain. So v in we know that what is v in, what is the voltage appearing across this input, it will be vs, and you are giving the feedback in the negative, it is a negative feedback. So vs minus vf, right? Vs minus vf. What is vf? Vf is beta v naught. So I will substitute vf as beta v naught. So vs minus beta v naught. This is what I get the equation for v in. Okay, now I have to derive the gain. So how do we find the gain? Okay, so gain is always written as a is equal to v out divided by v in, right? V out divided by v in. So v in we have already written. What is v in? Vs minus beta v naught. So when we take this in this way, so a into v in is equal to v out. So v out can be written as a into v in, that v in is vs minus beta v naught. Okay, so reorganizing, we get gain with feedback as, if you take v out divided by vs, we will get af, that is equal to the gain with feedback. So it is a divided by 1 plus beta a. So this is the gain with negative feedback. Okay, so this is the general result which applies to all types of feedback circuits. So the amplifier gain reduces by a factor of 1 plus beta a. This is how, when you apply negative feedback, the gain reduces by a factor of 1 plus beta a. So from this we can show that input impedance with feedback is, it is in series, right? So that's why it will be increased by this factor zi into 1 plus beta a. Output impedance will be reduced by the factor z divided by 1 plus beta a. Okay, and then you have to write the gain and bandwidth of the feedback amplifier. So as we have seen from the equation, the negative feedback amplifier reduces the amplifier gain. So therefore, as per the general principle, so since the gain is reduced, it should increase its bandwidth. In RC coupled amplifier, the gain reduces at low frequency and high frequency ends. Okay, so this in RC coupled amplifiers, the gain is shown as it reduces at low frequency and high frequency ends. So beta A naught is no longer much more than unity. So as a result, the percentage reduction in gain is less at two frequency ends compared to the midband. So the reduction in gain and increase in bandwidth of feedback, you can write is like this. That is, as F1 here, this frequency point is much lesser than f2, and f is much greater than 2f. Therefore bandwidth can be written as, so this is like f1 is much lesser than f2, and f1f, so this is f1f is much lesser than f2f. Okay, please note that it is f1f is much lesser than f2f. Therefore bandwidth is nearly equal to f2, and that is without negative feedback, and bandwidth will be equal to f2f. Okay, so if you see in this both equations, we can see that it is bandwidth is f2, and here also it is f2f. So from this we can say that it can be shown that a naught into f2 is equal to a naught f into f2f. So gain with feedback and gain bandwidth without feedback, so it is given as a naught into f2 is equal to a naught f into f2f. So we get the constant product of gain bandwidth. Okay, so for the derivation part of voltage series feedback amplifier, so you need to write the equation for gain, and then so draw this diagram. Okay, so this shows with feedback and without feedback how the gain is reduced, and how we how the gain is reduced, but and there is an increase in bandwidth. Okay, so that you have to write. So with this equation, that is constant product of gain bandwidth, you will end up this answer. Okay, so this is all about voltage series feedback amplifier. So voltage series feedback amplifier, the gain and bandwidth ratio, you have to write that constant product with feedback and without feedback. So that are the important questions that can be asked in this particular module, that is module 4. Okay, I hope you are clear with the problems whatever we have solved. Okay, any other queries you can ask me, and we will solve that. Thank you.